Okay, yeah, thank you to everybody on the committee for inviting me and for putting together such a nice program. I've really enjoyed it, I've learned a lot. So, starting with collaborators first, so all of the data that's real data you'll see is either due to the French climate modelling team, Volodina and those guys. They have two different climate modelling centres where they sort of work together in Toulouse and Paris. Or the Canadian team at CCCMA in Victoria. So all of the cool data is down to them. And then the sort of new methodology I'll talk about is stuff that Victoria Volodina has been working on. So she's a third year PhD student who wants to stay in the UK but wants to move to an even more exciting city than Exeter at the end of her PhD, and is great. So if you have any positions somewhere, contact me or her. Okay, so this is our Stats UQ group in Exeter. You might notice that nefarious stranger at the back. And Hussein's there, and Louise is here too. Great poster. And I'm showing this because there's Victoria. And just, you know, it's nice to show the people who have done this work. And in Exeter, we, particularly Peter's side, do a lot of stuff on health models and other kinds of engineering models. And then everything to do with my side is all about climate models. So 10 years of working with climate models, and I now have more respect than I ever did for them. So I'm going to spend maybe 20 minutes of the talk just talking about what climate models are and what the problems are. So this will be hopefully accessible, and then you can see the sorts of things that we have to try and throw at these problems. So this is a plot from the latest and greatest IPCC report, the Intergovernmental Panel on Climate Change. And this picture heavily influences policy. This picture heavily influenced the Paris Agreement. And what it is it's saying these are our sort of best guesses for what will happen to global mean temperature under various different scenarios of what we do with CO2. So this is, we just keep going like we are right now, and these are sort of, well, we'll maybe do something, and this is not quite as good as Paris, but something. And this is the sort of science we have, and of course we have it for more than temperature, and you look at lots of these plots. Okay, so these affect policy, but what I really want to show you are what is going on. So these tiny thin lines, they're climate models. A tiny thin line is a climate model. Now we've been talking about model runs and so forth a lot and building emulators, so model runs seem like nothing. I want you to think of each of these little lines as more than just a climate model. It's a country. It's a country's climate modeling effort over 6 to 10 years, up to the latest time that they have to submit their runs for consideration at the IPCC. So the UK is one of these lines. I think the US actually has two, one at GFDL, one at the community model. Most countries just have one. And they employ lots of people, yeah.
Does this graph discriminate in a way for ones which are known to be more accurate than others?
No. No, and there's also a trick. I mean, each of these models has actually subtracted the sort of model average, its own average over a certain period of time. So whilst it looks like they're tracking the data well, they're tracking an anomaly version of the data well, and some of them may be quite a few degrees off. But that's almost another story. Yes, so they're the endeavour of a country and a modelling group that may be dispersed over multiple cities. Are there any statisticians? Not in most of them, but there are lots and lots and lots of very smart people, mostly atmospheric or fluid dynamicists or physicists or what have you. Okay, so what they're used for is more than just policy documents. These data are publicly available. I mean, you need a fair few terabytes of space, but if you have one of these applications and models, the chances are that you've seen some of this data. So if you're interested in making decisions about your agriculture, or you have a sort of skiing resort in Aspen and you want to know how to plan resources for the future, or you have water models, or basically anything that might see climate, you're going to have some model that at some point is forced by what's going to happen in the future. How do you get that forcing? You probably downloaded the results of these simulations. So periodically, and I think the next time they're going to submit these things is next year, there's a deadline for all of the world's modelling centres to submit their collective endeavour over the last 6-10 years to the world, and then you get to use it. So it's open community site. Okay, so what is a climate model? A climate model is this thing, a generalized or global circulation model that is essentially, and really essentially, solving Navier-Stokes on a very coarse grid. So that's one grid box for the whole of the UK. And when you do that, of course, you don't really solve much of the things that are going to affect future climate. There's no clouds in those things. There's no many processes that you need to just sort of do a good job. So the climate modeling endeavor is not really about how you solve these equations. It's about what else you have to put in to make the thing do a good job. So when I talked about these teams of physicists, what are they doing? They're saying, okay, well, I know that the clouds operate in this way, so there's a group of them that work on maybe convection, and they do physics on smaller scales that try to describe what happens inside these grid boxes and try and sort of have some miniature solvers, if you like, making up for what's happening at sub-grid scale of the equations. So what do? Well, they'll write down maybe ordinary, maybe partial differential equations, maybe not that, maybe just sort of polynomials or whatever, and they'll use physical insight, and then they'll take data at certain parts of the globe and they'll try to get the curves to match it. It's not a machine learning exercise, because very much the principle is, if we're going to integrate this thing forward, then we have to at least be able to justify that this is based on sound physical principles. So you have 50 people, and 2 guys are working on their gravity wave drag scheme, and someone's working on their ocean mixing, and someone else is working on a different ocean mixing, and sometimes they talk. And when your parameterization, your little part of the model, when you think it's ready, it goes into the big model, and at some point someone, maybe one of the guys I put on the front of the slide, because they're kind of in charge of this, says, okay, it's time to put the thing together because we're getting up to the deadline. So you put all of these things together, and of course it looks terrible. So all of the different parameters that have been in these submodels, they've been optimized to see data at certain grid scales, and now they're seeing the combined model with all of its flaws and everything. So lots of things don't go very well. So the climate modelers call it tuning, where you try to sort of change the parameters. We call it calibration, I guess. And so they have a big calibration problem. Now, let's suppose they do their calibration and they've got about a year or so to do that. Then they're going to submit those runs to the IPCC, and then if you want to learn about Europe, you have to shove those model runs, like maybe you take a box of them, and they act as the boundary forcing for a regional version of the model on a much finer scale. And then if you're interested in your snow cap in Aspen, then you have to do a downscaling on those, and then you put them through your Aspen model. So there's a lot of chains of models subsequent to those things, but this is the main guy. This is the thing that's getting all of the global effects. Okay, so I talked about model tuning. Let's talk about how they do that. And if anything I say sounds like I'm criticizing the climate modelers, I'm not. They do a pretty much impossible job. So the full model, when coupled and spun up and so forth, will take 6 months to do those integrations. So that's kind of slow. What they will do instead is try to run short simulations and look at what they're saying, and then if things are going wrong, they can tell. So a short simulation is about 5 model years. This is going to be the Canadian model, and it takes about 4 days. So they'll have a meeting, say on a Tuesday, and they'll decide what they're going to do. And in the meeting, they'll look at pictures like this. So this is their anomaly deck. And they'll look at pictures like this. This is sea level pressure in their standard model, and they'll say, okay, well, we're trying to get rid of one of these blobs. I'll talk about those in a minute. What can we do? They make some decisions about moving one or two parameters, and then they're going to run the model again. So that's 4 days, and then they're going to see this thing. Okay, so what are these pictures? These are anomaly plots. So this is sea level pressure in the model minus the observations. And they color it so that in some sense white is all right. So if it's white, the model's sort of doing what it should be doing. And if there's a red blob, there's too much of whatever it is in the model, so too much pressure here. And if there's a blue, there's not enough. And so the tuning exercise is very much trying to get maps like this to look as white as they possibly can. Subject to some sort of physical intuition that here in the Himalayas, we don't really have the Himalayas in the model on those grid scales, so we don't mind missing the data there, so that's not a big deal. But this thing here and that thing there are particularly worrying. Okay, so it feels like I'm defining a standard kind of UQ problem, and so 10 years ago I thought so too, and many people have thought so since. And so you see a picture like this, and I tell you that they're moving 1 or 2 parameters at a time and then spending a weekend and then coming back and looking at pictures like this. And so you think, well, I can do a great job, and I'm almost 10s or 15s. I mean, it was definitely what I did when I first started doing this. I'm going to just go and do this better. So you argue, we can run a Latin hypercube, and you convince someone to do that, or maybe you do it on an old version of the model. And then you do a superb analysis, and you show that you can get a much better thing than this, super quick, and you give a talk to the climate modelers, and then they all put their hand up, and like if you've been in the room before, you know what they're all going to say, because they all have the same question with a slightly different wording at the end. And they say, okay, the pressure's good, but what happens to insert the name of my field that I care about that you haven't thought about? So this deck isn't just this picture. It's also zonally integrated sea level pressure. This is their file, by the way, so this is what they sit and look at. They look at all of these fields simultaneously. Global precipitation, zonally average precipitation, so this is showing that we're doing really bad in the equator. We've got too much rain in the equator. Cloud cover, so cloud cover is pretty bad, huh? According to their color scale, this is their thing. We have outgoing long wave radiation. So if you're getting that wrong, then in some sense you've got either too much or too little radiation leaving the planet. So maybe that's going to mess your climate change thing up. They have that for clear sky and ordinary. Long wave planetary albedo, I think that is. So that's how much light is reflected back of clouds or ice caps and so forth. That's pretty bad. I forget what a load of these things are now. Top of the atmosphere balance, I know what that is. So that's the net radiative flux. So red is too much heat coming in, blue is too much heat going out. Screen temperature, we definitely care about that, right? That's surface air temperature. So this is the thing that plagues them more than anything, this blob over North America. Doesn't seem to go away, even to my best efforts. So that's a problem if you've got a crop model in the Midwest or something, you want to know what's going to happen in the future. That's 8 degrees too warm. Okay, and we can carry on. There's one more I want to show you just because I think the colours are so pretty. No idea what it does. And then, of course, there are vertical things, so we don't just have a 2D surface. Yeah?
I'm confused. I've always been confused about this anomaly. Are you comparing with real data?
Yes.
So
Model minus data.
Minus actual. So where does the real data come from? So that just
Observations, satellites, ship programs in the ocean, sensors, and then those things are combined to make data products. So sometimes those are just like what they call optimal interpolation, what we call kriging.
Right.
But what they mean by that is there is no model, and sometimes when it's really bad, there's a data assimilation hiding behind it. So there's like a sort of numerical weather type model and things that we'll see.
But all that changes in time. Are you taking averages over time or something?
Yeah, so these are averages over time these are JJA, so summer. So they're looking at means because the dynamics are important, but you're actually assessing what the dynamics are is important. But the actual weather in the model isn't really comparable to observations because we don't know the initial conditions. that's the chaos problem. Okay, so the final thing is depth things. So you look at, you integrate over longitude, but you have levels. So up here, I think it's the stratosphere and so forth, so that you can see if there are biases in the atmosphere. And, well, we could go on, but they look at a lot of things at once. And I honestly, I know you're taking my word for it in some sense, but I've been in the room when they do this. They really do look at all of these things and discover why it might be wrong, because another 4 days of computation on the supercomputer is what's coming next, and they really want to tune the model. But, you know, 1 or 2 things at a time. So, whether we should calibrate or not is a different talk, and I'm not going to go into that. But certainly we could probably help using surrogates to stop this 4 days thing going on. So I spent a summer over there and tried to not just build a surrogate or an emulator for one field or for some metric, but for that whole series of plots. So here I have R, which has been conveniently shrunk, and in my environment you can see I have a load of things loaded that are to do with the emulator for this deck. So I can, for those of you who recognize R code, maybe I'll make it slightly bigger. Yeah, for those of you who recognize R code, I'll generate a 1,000-point design in the 13 parameters that we have, and I don't know, someone pick me a number between 1 and 1,000, just so that you see I didn't prepare it earlier.
1, 2, 3.
Sorry? 1, 2, 3. 1, 2, 3. So we'll pick the 123rd row and we'll give it that name just so you can see I didn't cheat. And so the idea is that I can have an emulator that is quicker than 4 days. It's running now. So it'll be a bit slow, but there it's done. And once we've run that, they can bring this thing up in their deck meeting. Let's have a look at it. There'll be a first page that gives them, wow, my Adobe really doesn't like me anymore. There'll be a first page that tells them, so these are all of the parameters, and red means we've increased the parameter from what they normally do, and blue means we've decreased it. So they're able to actually play around with this on sliders and do experiments one at a time. And then they can look at what the surrogate tells them is changed. So on the top they have what they had before, though now I had to redraw all of these pictures in R, so there are very slight differences. And here we have what the emulator saved. So it won't be very hard to find a field where I'm winning. So in fact, I'm just about there. The Southern Ocean is miles better in this particular prediction, and I think I'm doing better in South America, but perhaps there's some compensation. The UK is not so good, but the Canadians don't care about us. Okay, and then you look at precipitation, not doing so well, and so forth. And so they can try experiments and compare every single one of these fields using a surrogate, which is nice. So we've gone ahead and, seriously, this was quite a long time in my life. This is a really good run. Some of these are just red. This is the temperature. Some of them are just like we boiled the planet, which is nice because you don't want to waste supercomputer time on a boiling planet. Oh, and you have to, like, mimicking that color scheme is so much fun. Okay, fine. So that's that. What sits behind that sort of thing? So this is the scale of emulator that we like to build. This is what we're trying to do because it's really what they're interested in. It's going to be the most helpful thing. So to build such a surrogate, I want to build lots of univariate surrogates, lots of simple ones. So here's my slide on the equations of what an emulator is. And this is the slide. I only put this slide in because this is the one I showed to the modelers. Because they recognize this equation. They think of it as the Kalman filter. And of course, there must be 10 different versions in this room of what we think this is. I mean, Michael thinks it's the Bayes linear update, and some people think it's the update for the normal distribution, or it's the best linear unbiased predictor, or it's the orthogonal projection of, anyway. It's a nice piece of mathematics, so it's good to show it. The other thing to say is that I always fit some surface, perhaps a polynomial, perhaps something in Fourier functions in there, so we'll carry this thing along, and there'll be a fair few of these different types of kernel floating around, so we won't focus on that one too much because I'm going to change it anyway. Okay, so the Gaussian process is the workhorse, and I'm not going to talk, too many technical slides. Mainly we're going to look at what these things actually look like when you're trying to fit them in practice. So univariate GPs are nice and easy. Emulating the entire anomaly deck, so each one of those spatial pictures is 8,000 plus grid boxes, and there are sort of 20 odd of them, I can't remember. So if you wanted to do it the way we heard earlier in the week, the way Elaine's doing it, then that's 160,000 emulators. My code's not really good enough to do that, but even if it was, it doesn't seem like the right way to do it to me. Though it's fair to say there's certainly a tension within statistics of whether you should do that or whether you should do some sort of basis method. And I'm on the side of the basis method. So the idea is that you take the runs that you have and you do some sort of rotation of the Cartesian axes onto some basis. So SVD we've heard lots about all week, so you can use that. This paper's why we think that you shouldn't, but that's the talk I'll give next workshop. But whatever rotation you choose, in some sense that's arbitrary, in some sense you get to decide what you want from it. The idea is that once you take every run that you have and project it onto that basis, you get a series of coefficients. And if you're clever in your choice of basis, and the SVD is one such choice, then you'll only need a small number of those coefficients to reconstruct the whole picture when you sort of combine the basis vectors with the coefficients. So you boil down a big spatial field into a bunch of coefficients, a small number of them, that you can build single emulators for. So that's going to take it from 160,000 to maybe tens or 100 or a few hundred at most. And then you still get nice spatially coherent pictures. Okay, so that's been, Dave Higdon started this in statistics. I'm sure it was around much longer than that. Okay, so if I'm going to build tens or hundreds of emulators, I want something off the shelf, or I want to make something, put it on the shelf, and then keep taking it down and using it off the shelf or out of the box. When you try and fit the stationary process, which is about as off the shelf as you can get, and I'm sure people might be using Gauss-Krieging, people might have written their own code, but now they just use the same thing every time. When you do this tens or hundreds of times for one model, and you start looking at diagnostics, you often, not just occasionally, but often, maybe 20% of the time, run into diagnostic problems with the stationarity. And so the question is, what do you do about that? And that's the subject that Victoria's been working on. Okay, so let's first step back, because we're two communities in the room, and perhaps not everybody's messed around with diagnostics for Gaussian processes. So let's look at what a good set of plots would look like. So to look at what's good, we'll just pick a Gaussian process. We'll actually sample 4 different processes, and we'll run a small Latin hypercube in them, and then we'll fit emulators and look at the diagnostics. So we'll see what good looks like. So this is good. This is what we call a leave one out plot. So what you do is you take each run out of the design one at a time, you refit the emulator, and that gives you a black dot, a mean, and then an error bar, or a sort of 95% prediction, and then you've got the truth over it. And we always colour it green if it hit the error bar, and red if it's outside, as a sort of quick visual, are there any major issues? Of course you should expect maybe 1 red dot in 20 if that's a 95% bar. And this is good. You might worry about this one here, but actually if you're on the edge of the convex hull of your design set, as this point clearly appears on the edge, then we don't worry so much, because this is more of an extrapolation. So we know that the uncertainty is an extrapolation problem. But if you're seeing this in the middle of your points, then, and there's lots of them, maybe you should worry. You shouldn't just look at leave one outs. So actually the main thing that we like are essentially standard error plots. So what you do is you, just like the old regression residuals, you take your run, you subtract your emulator prediction and you divide by the standard deviation, and that should give you a patternless, homogeneous cloud of points, roughly between these things. And so if you see more variance at one end or another, or you see some sort of pattern, then that's indicating that there's something wrong with your stationarity. And the question is, if you're seeing that, what is it and how do you fix it? But anyway, this is all good, and this is the other variable in these things, it's all good. So let's look at one of the canonical non-stationary functions that people test to see if their non-stationary method works. Now, I'm not sure which paper this first appeared in. I actually think they set this up to sort of cheat Bobby's TGP, really, but maybe I'll come on to that in a minute. Certainly I didn't come up with it. It's a bit mean, really, to poor old TGP. So it's non-stationary in the sense that things are much highly correlated and then it smooths out at the end. And it's kind of like a sine wave that as you move along the line x1 equals x2, the variability decreases and the correlation gets larger. Okay, so if you stuff the out-of-the-box stationary emulator onto that, as we did, you get diagnostics that look like this. Okay, so we heard a talk earlier in the week that said, well, we'll only look at the emulator if more than 5% of our things miss the error bars, so more than 5% red dots. So this passes. This is fine by that particular automatic procedure. But if you look carefully, look how close the truth is to our mean prediction everywhere on this side, on these sides of the plots, and yet how big our error bars are. We're underconfident over here. I mean, it's more difficult to see in these types of plots, but when you look at our standard error things, you notice the variance decreasing. And if we drew this on the line x1 equals x2, it would be stark. Okay, so you can then fit the surface with that thing and you see how bumpy things are at the top. And then even more worryingly, but almost obvious from the diagnostics, the variance plot looks like this. So red is where we've shrunk the variance to 0 from the points, and you can see that we only learn anything about the surface in a really localized area, and everything else we're still uncertain about. So we're wasting quite a lot of information. So why would you care? So I put this up because we've seen plenty of calibration this week, and you might have your favorite way of doing it. But Aretha's talk was talking about this kind of thing, and she was emulating the negative log likelihood, which is that. That's also the history matching implausibility. And either way, if you're history matching, you're cutting out space if this thing is large, and you're keeping it if not. And if you're calibrating, you're using this to find the best setting of the parameters. And inside this variance is the uncertainty on your emulator. Okay? And so if that thing is big, you're going to have diffuse posteriors on your calibration parameters, or you're just not going to be able to rule out any space. I mean, that's sort of obvious from this picture, right? I mean, if I draw the observations on here or on here, we mostly can't really tell anything about the parameter space because we're just so uncertain everywhere. Okay. So, non-stationary GPs, what can you do about that? So the first alternative that people have proposed and advocated for in computer experiments is plow everything you can into the mean function. So fit a huge order polynomial plus a huge order as much as you can in here, and then the residual will be stationary. So that's the argument. It doesn't really work in practice, but I'm shaming myself because I used to say that it did. So there's my argument for it did. The thing is, I spent so much of my time, particularly with this Canadian example, looking at plots that didn't look right and trying to think, okay, so maybe if I put that kind of term in to fix that, oh, it fits, it doesn't work, oh, it doesn't. You spend too much time by hand trying stuff out and most of the time not succeeding. So maybe that makes me a bad statistician, but it certainly isn't good if I want to hand my code over to the climate modelers to do this for themselves. Now, the spatial statisticians in some sense are on my side. They would say you should put more effort into the kernel. So, okay. Then we have composite Gaussian processing. Okay, so This is Bar and Joseph, there's a reference at the end. And this sort of takes this idea to the nth degree and says, okay, well, let's say we're not going to do lots of statistics and think of a really tough regression, but we'll just say there's a global Gaussian process and then a stationary residual. So you just get the sum of two processes. There's an existing R package, so we're going to compare what we're doing to that, so that's nice. So you can do it. I just worry about how rich this is. I mean, it still requires stationarity locally, and I don't really believe that. Okay, then there's Bobby's TGP. Okay, so I'm not going to be mean to TGP. That's not fair. Plus, Victoria is A, watching, and B, sent me an email asking me to get Bobby to sign her a t-shirt. So we're big fans. This package is fast and almost unbreakable and does lots of cool stuff. So what it's doing, as John Paul talked about on Tuesday, is it cuts up the parameter space along the Cartesian axes and fits Gaussian processes into the different spaces. And then I think there's a BMA step that sort of makes things a bit less discontinuous. I still find it a little bit difficult to interpret, in the sense that I feel as I get towards the edge of one of these boundaries, the stuff from the neighboring regions should start to tell me things that are going on. Okay. And then there are parameter space deformation methods, so Montagner and Toctar. They don't have a package, so it's difficult to compare with what they're doing. The idea is you extend the input space by one dimension, and you make that extension a Gaussian process, and you fit a stationary thing to the normal process in G. So the extended function is still stationary, so you can do that easily, but the marginal isn't. Okay, so that's like cool maths, I guess, but I find it hard to get my head around. So
Redis code, if you want to try it, this is, I mean, it's not 2006, it's like 2001 NIPS. But
yeah,
so
no, we've written our own code, but
yeah.
it's not really
There's
fair
no
for us
R
to
code
compare
available.
against it. Yeah,
Yeah.
well, R is
Yeah.
the main thing, right? Okay, so let's consider. So we're going to do something a bit like TGP. Sorry, everything's a bit like TGP. So consider the tree Gaussian process. It finds these different regions, and then it fits a stationary process within that region. Okay, so that's what that model would look like. You have L different regions, and then you fit a process, and that's like a nugget process on the end. So what we're going to do is allow runs that aren't in a particular region to have an influence on what goes on in that region by essentially mixing them. So we still have an idea that there is a GP in each region, but our function at any point is a mixture of them. Okay, so that's not a particularly new idea in spatial statistics. The way we do it's a bit different, but yeah, that's the idea. So you're saying that things are a mixture of processes. Okay, so these lambdas are mixing weights. They depend on the parameters, and of course they're greater than 0 and they sum to 1. That's the simplex thing. And then you have something that only the nugget from the region that you think you're in actually influences the fit. So there's another way to write that as a mixture of kernels. So your model, given your parameters and crucially given these weights, is a GP, and it's got this mean function again. I always carry that around, and then the kernel is a sort of sum of these stationary kernels. So it's kind of a mixture of kernels. Fine. So that's the model. So you say, okay, there are these processes flying around, and then my evaluation is just a mixture of those, and that's going to get me some non-stationarity. But it's conditioned on these things, so we're going to have to figure out how to fit these mixing weights. Okay, so the first thing that you would try if you're a statistician is some sort of categorical regression. So I've got L different regions. I want to see if a parameter choice is more likely to be in one region or another. So I fit a categorical type regression. I mean, you could use a GP classifier or what have you, and that's going to have some parameters in it. And so you then, in principle, you could construct the joint distribution of all of those parameters given L, and then you can use some clever algorithm to figure out how many L's you need, maybe reversible jump MCMC, maybe you just do it by BIC or some sort of marginal likelihood based thing. Okay, so the thing with that is, firstly, we're trying it. I mean, it seems hard. Anything when you say reversible jump MCMC seems hard, at least to me. So is there something, we're looking at it, definitely, but there's identifiability to consider. But is there something a little bit more intuitive, something a bit more linked to what we actually do? So this is the way I tend to think of things is I'm trying to do this problem, I'm looking at these diagnostics, they're wrong in a certain way. Is there something about that information that I can bring into solving it? And is there something about that that I can make automatic? Okay, so if I consider instead an interpretation of these mixing weights as probabilities, they're probabilities that I'm in one of these L regions. Okay, that's kind of normal. And I consider the out-of-the-box stationary emulator. So I have a first pass where I'm going to fit a stationary emulator, because that's in fact what I'm going to do. And I think about those standardized errors that I've been plotting. Okay, so the truth minus my out-of-the-box stationary emulator divided by the variance with that run taken out. So they're a kind of random quantity that I can start thinking about. And so in a nutshell, what we do is we try to cluster these into regions of similar variance. Okay, so that's a kind of simple model. For the statisticians, this is like, why are you putting this up on the slide? But let's just go with how the statisticians do this kind of thing. So we come up with what we call a latent process, which is not real, but it's an idea that the truth is, for each parameter choice, there is a true cluster that function belongs to, a true Gaussian process it belongs to, and we don't know what it is, so it has certain probabilities, so it's multinomial with those probabilities. And then we say if we knew what cluster it was, the standard error would be normal with some variance, and then you can have the categorical regression model for the probabilities. And as long as you put some sort of condition in the prior, like an ordering on the variances, you can do a posterior inference on the alphas, and that's going to give you lambdas and these variances. Okay, so that's what the model looks like. We use Stan to fit these things, and Stan doesn't deal well with discrete parameters. So Stan is Hamiltonian Monte Carlo, and it means that you can do MCMC and it tunes it for you automatically, which is nice because tuning MCMC by hand is painful. It's also nice because you can try lots and lots of different priors and you don't have to worry really hard about whether things are going to work. But it doesn't handle discrete, so we integrate these things out. So in some sense it's like, it's not real, but it goes away anyway. Fine. So what you do is you can take my word for it that you can just do MCMC on those quantities. You get these errors from the stationary fit. You can do MCMC, and then you have a bunch of samples of alpha and these things, and that allows you to compute lambdas for all of those samples, and you can take an average, and that gives you an estimate. Okay. Or you could, so that's a posterior expectation estimate. You could use a map estimate. You could use what have you. So with representative samples, we can get estimates of this thing. And so what we're doing is specifically using the diagnostics that we're always looking at to cluster in some sense. And then so when we look at the diagnostics, we can say, well, maybe I'll try this, and out of the box it should work quickly. So let's just do it. So 20 slides, 20 pictures, I think. So this is the wavy function again. And what we're doing is we're coloring the runs that we have by the posterior weights. So blue means that I'm in region 1, red means that I'm in region 2, and then when it's purple, there's a sort of mixing there. So this is like 100% in region 1, and this is like a kind of 50% in region 1 and 2, and this is about 80% in region 2, and that's in region 2. So this is what the mixture model gives us in the posterior. So you can see, if you think back to the wavy function, when it's really rough on the lower diagonal, we're getting one type of behaviour. When it's really smooth, we're getting another, and the transition is handled by this mixing. So now for comparison. So first I'll tell you what this plot is, and then I'll explain how we produce it. So you have stationary, you have our non-stationary method, TGP and CGP. The packages are available on CRAN. So stationary we've seen before, these two pictures. And then this is the cross-section x1 equals x2, so along there, and how the mean and the standard error goes with the truth being a dashed line. So you can compare how we're doing for yourself, but the important thing to say is that Victoria is brilliant in this sense. We don't do any cherry picking. So we have a version of this coded up that we just apply every time, and we're applying ours out of the box, and we've applied everyone else's out of the box. So we're going to apply it to lots and lots of examples. Every time we've done it, we didn't change anything, we just pressed enter. So sometimes it gives answers that aren't, as good as we could make them. So if you're, I don't know, the author of TGP and you want to argue that you could do better, yes. and I agree that you could, and we could too, but just as a fair comparison. So the idea isn't that we're better in any sense. That's not the point. The point is that it has the not totally daft property. So we run it, it gives something sensible. If it does that enough, and there's a statistical intuition for why we're doing it, then we're confident to apply it to our 100 emulated problems. So this isn't like, look at my cherry pick thing doing better than everything. This is our out of the box is roughly sensible. Okay, so it's definitely sensible here, and it has this nice property that we've got low variance in the smooth area. That's nice. But it's a bit mean on TGP, like I said. So let's do something that's much fairer to TGP. So we take a 5D function, and we make one of the dimensions, x5, have this sort of multiple sine wave type behavior. So the correlation is really high here, and then it's really low over here, and there are 5 separate regions, and in these little blue things we just sort of blend things so everything's continuous. Okay, and we're going to compare our methods, all of the methods, with a much harder comparison than leave one out. So we're going to leave a whole Latin hypercube out. So we construct our design via a kind of sliced Latin hypercube. So a sliced Latin hypercube is where you have a Latin hypercube that's made up of lots of Latin hypercubes. And a K-extended one is a version of that that we use in climate models where the first Latin, they're designed sequentially. So a sliced Latin hypercube is designed jointly. The extended one starts with one and then builds it up so that we explain as much as we can as we go. And the reason for doing that is when you run a batch job on a supercomputer, you have a wish list, but they're not going to give you all of the runs back. So you try to maximize what you're getting at every stage. So what you can do with this type of design is say, fit it to 3/4 of the data, and what's left is a Latin hypercube, so you have a space-filling design left out. Can you predict that? And then you do it for all of the different Latin hypercubes you have. Okay, so out-of-the-box stationary gives these diagnostics, as you would expect. Lots of variance here at the end. And our procedure selected 2 clusters, not 5, so this is just out of the box. And it's sort of doing what you expect, and there's this blending region in here when really we probably need 5 clusters, but let's not cheat. And here's the comparison over all 4 methods are in the columns again, and the rows are, there are 4 different Latin hypercubes that we're estimating. So these are joint, they're not leave one outs, the whole thing has, the emulator's never seen the whole thing and it's doing it jointly. And actually I'm kind of surprised that TGP wasn't so good here. It's perhaps because we didn't have many runs in the really high varying regions. So we tried to be fair, and I think we've screwed it again, so that's our fault. But we're surprised that we do nicely in the smooth region anyway. And you can see actually stationary's okay, but its error bars are really large in the smooth region. Okay. So this is another picture from Gramercy and Lee's paper where they're talking about needing nuggets to fit processes where you have this sort of non-stationary behavior. Because you can't really sample this densely enough, but when you sample this, you sort of pin down the whole function and it looks weird. And indeed, I think this is a reproduction of what they did. But when you do a stationary fit without a nugget, it does look weird. And the standard error plot has this shrinking over here, which our mixture thing captures, and the non-stationary model decides that it wants to put a different nugget over here and a different thing rather than a correlation length, which is fine. So the comparison of the four stationaries here, I mean, with a nugget this would be better, but it would be a uniform nugget everywhere. Ours has this nugget, but the nugget's allowed to change in the different clustered regions and get, the nugget's not blended, so that's kind of important. And then TGP does quite well here. So. Fine, and then just to wind up, let's do it for real. So with the French climate modelers, we have the HiTune project where they're trying to tune their convection scheme to lots of different parts. So the convection needs to be different over the ocean than it is over the desert, over land, because of the sort of boundary layer properties. So they want this online tuning to help, and they won a pot of money that lets them work on this for 2 years and have us over to France to play on these sort of coding sprints. And what's cool about these is that they sit in the room and they run the model right there live, and then they try to fit the emulators with us. So we develop the code and pass it over and do training, and then when we can't do something, we go away and try and do it better so that they can. And so when we first ran the CNRM model, we're doing 2 models at once, we had this picture, and there are 9 parameters, and one of them sort of blows up to the end. So Victoria's like, yeah, it's non-stationary. Sorry, Victoria. True story. So I've had these before and not really done very well trying to get exponentials and stuff, and it doesn't really work. But Victoria's method is nice. So the stationary leave one outs are okay. There are a few red dots there. This is a whole Latin hypercube left out, and you can see that we're always going wrong in this region, as you would expect. It's a systematic problem with our error specification. The mixture comes out. There are a few red dots in this region, but that's because we're in a 9-dimensional space, so there are a few parameters having an influence on which group you're in. And then our fit seems to do better, at least in this region, with a large variance. And just to compare all of the 4 methods again, so we have stationary hours, TGP, CGP. Our error bars are in some sense the biggest, but here you can see actually we're capturing points that are right on the edge. So maybe this is what's going on, and they all do okay, I guess. So that's that. So we want to give tools to climate modelers to help them in these tuning rooms. But to do that for real takes weeks of time anyway, but fitting these emulators. And if you wanted to do it for 160,000, there would be tons of work. And diagnostic checks fail all the time in the ways that I've shown you. So what we want is something that's fast, flexible, and off the shelf. I could always do a better job given enough time, but I guess I just don't have enough time. And really, we want the modelers to be able to do it. So I argue that these mixtures are intuitive, they're diagnostic-led, so in some sense they make sense to me. We're fairly competitive, and there are plenty of next steps in doing it even better. So if you want to read more about the spatial emulation approach, that's on arXiv. More on climate model tuning here, emulator diagnostics, the different kinds of non-stationary stuff, and there's code to build your own k-extended Latin hypercubes there if you like it. Okay, thank you.
Any question? Yes?
So first, thank you for the wonderful presentation. I've learned a lot. One question I have is about the cross-validation standardized residuals. It looks like you're looking at them without decorrelating. So these guys are correlated.
Yes.
Under the model assumptions. So shouldn't we decorate them before speaking of 5% rule?
Perhaps. I would have to think about that one actually. I always want to say that they're not, but I'm imagining that you're right and I'm wrong. So I'm not going to say that. I think I may even have written the wrong statistic up. They may be decorrelated already.
in the Bastos-O'Hagan paper, there's a way of doing that, which picks out the most sensitive ones first.
Yeah, I actually think the pivoting thing, I think we've actually done that, and I'm just not giving Victoria credit for doing it, so my bad.
So do you always emulate the whole over the whole parameter space, or do you ever use the knowledge that, in fact, that certain choices of parameter are going to give you bad fits in other pictures, so it's not actually worth building the emulator for that?
If they had knowledge that certain choices of the parameters are going to give bad fits, then they wouldn't be in our initial set.
Yeah, but they don't start off being. But surely, if you're, I tend to do these things progressively as a history match.
Of course.
So I would try and match. So rather than matching everything initially, I would sort of progressively try to reduce my parameter space, which means that a lot of the complications of the behaviour sort of gradually get sort of spinned down a bit.
So there's a pathological unwillingness to let go of parameter space in the climate model community, because the question is there a set of pictures where things are looking good? And that doesn't mean that they would accept those parameters, but they would like to know, because they would like to find out why, and they would like to then go back to those parameterizations and mess around. So the fundamental problem with cutting out space that they have is that they don't know the structural error. The whole point of talking to me is they want to know it. But plagued by identifiability, I need to start giving them tools. And every time I give them a tool that does some of it, they say, oh yeah, but there's all this other stuff over here. And so this, in fact, that Canadian example was me losing patience and just saying, give me it all, and we'll do it all. And then you can't come to me and say, well, what about this? So yeah, once you get to the point where you can really cut space out, great.
Well, and the question is, is there no level of structural error that they're prepared to sort of claim to?
Well, the thing is, the structural error is so spatially dependent.
Yes.
And in a sense, I'm a victim of my own success. So I have papers where these blobs that they thought were structural and you could never fix, we went in and fixed, just with vanilla history matching. And then there are things that we've shown that there's nothing that you can do, it's always there. So in some sense, they just want to know, well, which is which? But putting structural error spatially is a hard problem, because how do you tell that it's really a blob of red always, and it's not just the parameter choices? And we're working with like 60 odd runs rather than 1,000, so it's difficult.
Just a quick.
Yeah, mine's just really quick. Are you emulating the field or the anomaly field?
The field, and then subtracting the observations from that. Yeah.
Just a very old-fashioned question. What about half-normal plots when you do your diagnostic? I mean, they're fantastically used in other areas like quality improvement. And
Half normal. There's probably another name I know that by. What does that plot look like?
You plot the residual normalized, which
Mhm.
you mentioned, against the expected order statistics from a normal.
Oh, the QQ plots.
QQ
Yes.
plot,
Yeah.
QQ, I call them half QQ.
Yeah. Yes, I knew. No, we haven't. We don't do that routinely. But yeah, that would be cool. Maybe we'd have to think about David's comment there.
Because then you go in and home in very easily on the anomalies.
Yeah.
And then you could label the anomalies if they're close in space, for example. You'd
Yep.
see them, and that would meet David's point about
Yep.
local correlation
Yep.
and so on. So,
They tend to characterize transformations of the output.
and transfer, yeah. Whatever. QQ. So.
You guys like transform any of the inputs so that you end up with something that's stationary against the transformation. That's all. That can be quite an easy way to make something immediately.
Well, of
stationary,
course.
right?
So this is back to the thing that I showed here, right? That one.
Yeah, that's one.
And in fact, that paper, I did just that. Yeah, if you can find the transformation, if you've got time.
Yeah.
In that particular paper, I had like 4 things to do. So, I could really hammer it and I was also a postdoc, so I had far too much time. The the old methods of statistics work. I'm not saying they don't. I'm just saying when it's out of the box and it's so many things, you know, is that really the right approach?
I mean, so to follow up on that, I mean, if say you were fitting this complex response, if that is changing for your system every time you're fitting it, then there's something going a bit wrong, isn't there? Because there really ought to be these kind of general behaviours in these models, right? And then so eventually you shouldn't have to be searching this massive number of combinations for your complex response every time.
So in this application, only 13 parameters in the Hadley Centre 127, but when you fit an emulator, you allow it to see all of the parameters, but it's really a subsurface in a few of those dimensions because you just don't have the data. So, and you're doing this for lots of different things. So some parameters do nothing to temperature, but maybe doing something to the cloud cover or what have you. I mean, yes, a permanent deformation of the parameters might help, but
well, permanent
maybe.
in the sense of some sort of basis, but not, you know, it's never like you don't fit it.
You never get the same mean function across different emulators. And you also, well, bear in mind, you're also emulating coefficients of basis functions, which don't have the same relationship as say, the model output would to the inputs that's gone through a transformation, a projection.
So do you keep these though? I mean, because you seem to leave them in the later.
Oh, I still fit the surface,
Yeah.
but I have an automatic procedure for doing that, and that's what I permit myself. So it takes a few seconds to fit the best surface I can fit with the things that I let it do, but I can't allow arbitrary transformations of all parameters. I suppose I could write really awesome code that could do that.
You
but
wouldn't
I
want it
haven't.
to be arbitrary every time, though. That's what the point I was just making. If it were arbitrary every time, that would be really daft in a way, wouldn't it? So, okay, but thank you. That's
Okay, very last because.
So the classical way to do this problem in spatial statistics is the Sampson and Gottlob thing, where they warp space to mix space stationary. They do all the inference in the stationary space. I don't think it's quite what's done here. And then they warp back.
Yeah.
Has anyone? I mean, I don't think that doesn't look like the Sampson and Gottlob formula.
Yeah, okay, well I think it might be inspired by that because essentially that marginalization is walking back, isn't it? Perhaps this is a more Bayesian version of what's probably a
I don't
classical
know that
version.
paper, but the Sampson and Gottlob thing, you just warp space so that they don't have to have that extra. They don't have that extra dimension. They only need that extra dimension sometimes.
Yeah.
If they can't do the warp.
Never tried it.
I just wonder whether, I suspect in doing that in 13 dimensions is just really hard.
Well, I think that when we get reviews, when we put this paper in, we might have to do it, so I won't let them send it to you.
So, on that note, let's try to get back on time. Just behind the.